And basically what this KSP says is that there's an equilibrium between the solid in solution and the things that have dissolved, the aqueous species. And same rules apply for this K. We don't include solid species in the K for this equilibrium expression. And so we can fairly readily write an equilibrium expression for instance, the solubility of calcium iodate. So if we write that out, get my purple color here, KSP is going to be equal to the concentration of the calcium ion times the concentration of the iodate ion. And because that has a stoichiometric coefficient of 2, we need to split that. Nothing new here really. The only new thing is that we have a solid on the reactant side. We don't include solids in our equilibrium. We saw that before. Squaring stoichiometric coefficients for the powers is that before? Yep. Yeah. We're going to mostly be seeing solids on the reactant side at this point. So hopefully writing these KSPs are going to be second nature to you at this point. So we also can think back to chapter 13, I believe it was, where we were looking at solubility and doing calculations with that. And so if we know a solubility of a solution, this is in grams per liter, we can calculate what we refer to as a molar solubility, where that is just a unit of moles per liter in terms of solubility, okay? So for this problem, again, we're just sort of refreshing our minds on what we've done in the past on soluble things, solubility. And so calcium oxalate here is a slightly soluble salt at 25 degrees Celsius. The solubility is 0.0061 grams per liter. That's very small. And so we can determine the molar solubility in moles per liter. And so this is just dimensional analysis. We have our 0.0061 grams per liter of the solubility. And this is grams of calcium oxalate per liter of solution. And we can use the molar mass to go from grams in the numerator to moles in the numerator. So for every 1 mole of calcium oxalate, there's 128 grams. And so we can find that the molar solubility is 4.8 times 10 to the minus 5 moles per liter. So again, not much new here except maybe a refresher on the term molar solubility. I don't know if we use that very much in chapter 13. Okay. Everyone okay with that? All right. But now we get to some new things. So what are we going to do with our molar solubility? Well, if we know the molar solubility of a salt, we can determine its KSP. We can determine the solubility product constant. So from our molar solubility of calcium oxalate, which we determined was 4.8 times 10 to the minus 5 moles per liter, we can calculate the solubility product constant. In order to do that, we need to write out our equilibrium. So we're going to have calcium oxalate, solid, in equilibrium with calcium 2+, and the oxalate ion C2O4 2-. This is maybe an ion that you don't see very often, and it's kind of, it's a little different on nitrate. That one's kind of obvious. You've seen that one a lot. C2O4 2- is the oxalate ion. I would kind of keep this one in your memory. This oxalate tends to show up in this chapter for whatever reason. Okay, so we can write a KSP for this equilibrium. KSP equals concentration of calcium times oxalate. And everything has a stoichiometric coefficient of 1. If we set up an ICE table for this, let me move this, maybe. Nope. Okay. If we set up an ICE table for our calcium oxalate solubility, just like we've done with other equilibria, what do we initially have in solution? We have solids, yeah. And so we're going to assume that we've not formed any of the products, any of the ions. So initially we're going to have 0 moles per liter of both the calcium and the oxalate. And so in order to reach equilibrium, we have to form some amount of the calcium ion and the oxalate ion. Which means that at equilibrium, we're going to have X moles per liter of calcium and X moles per liter of oxalate. We know the molar solubility of calcium oxalate. How do we get that? How does that become a useful number for solving the KSP? It may not be obvious, and that's fine. It's kind of a weird concept. But that molar solubility is actually equal to X, right? Moles per liter. So we're going to do a few examples of this, but keep in mind that if you're given a molar solubility, that is equal to X in your equilibrium constant expression. Okay. What this says for this specific problem is that when we dissolve calcium oxalate and it gets to equilibrium, we're going to have 4.8 times 10 to the minus 5 moles per liter of calcium ion and 4.8 times 10 to the minus 5 moles per liter of oxalate ion in solution. Okay. So our KSP then is equal to X squared. So I'm just plugging in our values for calcium and oxalate into our KSP expression. KSP is equal to X squared. We know what X is. (4.8 times 10 to the minus 5). So we square that. And so our KSP is equal to 2.3 times 10 to the minus 9. Okay with that? Relatively straightforward. Molar solubility is X. That's the main key here. Questions? Okay. So let's look at another example. Now we're given a KSP. I want to calculate the molar solubility of calcium iodate. Okay. So we'll write out the equilibrium together and then I'll have you work on that individually or with your neighbor, that's fine too. So we'll do our calcium iodate. That's going to be a solid in equilibrium with the calcium 2 plus, aqueous plus 2IO3 minus. So from here, work with your neighbor, work by yourself to calculate the molar solubility. I'll just take a minute or two. Yeah.
Was there calculators
After the exam? If there was, it would be in class 1. You could use the half. It's under the. Yeah. All right. How's this problem? Does it feel difficult? So, in order to solve molar solubility, given a KSP, you're basically solving for X, right? We said molar solubility is X. So we can set up an ice table, just like we've done many times in the past. Because we have 2 iodate, don't forget to drop that 2 down into your ice table. And when you set up your KSP, so we're going to have calcium 2 plus times the iodate squared. And again, keep that 2x inside the parentheses. And so you should end up with 4x cubed for your KSP, which is equal to 7.1 times 10 to the minus 7. Right. And you can solve for x. Divide by 4, take the cube root. Should get 0.0056 moles per liter. Were we successful? Okay. Yeah, so this is very similar to what we've been doing. The main difference here with these solubility questions is that your reactant is going to be a solid for the most part.
So then you don't have to put anything on the bottom.
You don't have to divide by anything. Yes?
So for the equation, if the coefficient is 2, we take it, we'll end up with 2x and we'll also take it so to square it.
Yes. Yes. So if you have a 2x in your ice table, you're going to have to make sure you square that, which gives you 4x squared times that other x. So whenever you have, you're going to see this happen frequently. Whenever you have in your ice table an x and a 2x, you're going to end up with KSP equals 4x cubed. And you're going to see these patterns, right? So if you have, we'll do a couple examples later on. Yeah, any other questions? Yes, Naomi.
Do we know that it's a solid for our equilibrium equation because it's soluble? We just have to
Yeah, so the question is, do you know it's a solid because, what did you say?
It's soluble.
Because it's insoluble. Yeah, yeah. So when we have a slightly soluble, or what we've previously referred to as an insoluble salt, we're going to put it as a solid on the reactant side. And the other clue, you know, typically when you see molar solubility, this is going to be this type of equilibrium. Other questions before we go on? Okay. This one, think about what you would put in here. I'm going right to the equilibrium line. So we have briefly mentioned in the past the common ion effect. And basically what this means is that you have an equilibrium and an ion gets added to the solution that shows up in that equilibrium, and it affects the equilibrium. And this is all Le Chatelier's principle, okay? So here we have a silver bromide solid with a KSP, and we want to know its solubility if we add 0.1 molar KBr to that solution. So I mentioned that you don't necessarily have to recall all of your solubility rules, but here's an example of why it's important to at least recall a good number of them. You have to recognize that KBr is completely soluble. It's not going to have an equilibrium. Okay? Silver bromide, AgBr, that's going to have the equilibrium. The KBr, it completely dissociates, and we're effectively adding a common ion, a bromide ion, to the solution. Okay? So if you have your silver bromide equilibrium, forming silver ion and bromide ion, and we add some amount of bromide, what do you expect to happen to the equilibrium? Which way does it shift? Reactants or products? Reactants. Y'all are going in that direction, which means this. Okay. Yes. Good. Yeah, so keep that in mind, right? So we're going to shift the equilibrium towards the reactant side, which means this silver bromide becomes even less soluble. Okay. So to solve a problem like this, we're going to set up another ice table. The only difference now between this and the problem we just did is that we're going to have an initial concentration of bromide ion, and that's coming from the KBr salt. So for our KBr, this completely dissociates to potassium ion and bromide ion, not in equilibrium. So for every 1 KBr, you get 1 bromide ion based on the stoichiometry of the formula. Okay. Everyone see that? Okay. So we have an initial concentration of bromide, but still 0 moles per liter of the silver initially. Okay. And the rest just follows through like we normally do with our ice tables. We're going to have plus some amount X for silver, plus some amount X for bromide. And at equilibrium, we'll have X moles per liter of silver ion and 0.1 plus X for bromide ion. So we can set this up all equal to a KSP, which is the silver ion times the bromide ion. So that means it's X times 0.1 plus X. And that's all equal to 5.0 times 10 to the minus 13. You have 2 options. Just like you did with the acid base. You can solve quadratic, or we can assume that X is small. Let's assume that's what we know that X is going to be small because our KSP is tiny, times 10 to the minus 13. Okay. Very little amount of bromide is going to form in solution, even if we didn't have excess bromide. Okay, so that's going to go away, and we're going to have, I'm going to move my 5.0 times 10 to the minus 13 to the other side, probably just to confuse you, 0.10 times X. And so when we solve for X, we'll get 5 times 10 to the minus 12. Excuse me. And that is moles per liter. And so you can see if we were to add 0.1 plus 5 times 10 to the minus 12, we would still end up with 0.1, right? So we have made a decent assumption that X is small. Questions on that? So we can also show that the solubility has decreased and that your prediction that the equilibrium shifts towards the reactants is correct simply by solving for the solubility of silver bromide when there's no excess bromide or no added bromide. And so we would have KSP equals silver ion times bromide ion, which would be equal to X squared. Everyone okay with that? If I jump right down to the equilibrium. Okay. Still equal to 5 times 10 to the minus 13. And when you solve for X, you get X equals 7.1 times 10 to the minus 7 moles per liter. So without that 0.1 molar bromide, we've got 7.1 times 10 to the minus 7 moles per liter in terms of the solubility, which is tiny. But by adding just that small amount of bromide, we go down by 5 orders of magnitude. Okay. Yes?
For the question,
Mhm.
it says like what's the solubility, so do we have to convert to molar solubility? Like grams per liter?
That's a good question. I think for this, since I didn't say you could leave it in moles per liter, a better question might have specify the units or at least the answer. I think mostly we stay, trying to think about the homework. I think a lot of it is still in moles per liter, but it's fair. It's a fair question to have to convert back to grams per liter, I guess. Fair but annoying. Other questions? Okay. Our ice table. Let's go to this. All right, so let's take a look at these 3 lead salts. We have lead carbonate, lead sulfide, and lead sulfate, and their KSPs. And let's determine which one has the greatest molar solubility in water.
Dr. Carnes,
Yeah.
so just off of her question,
Mhm.
the units for like, if it just asks what's molar solubility, it's moles per liter?
Yes.
And then if it doesn't necessarily specify that, then we could
So if it's molar solubility, it's definitely moles per liter. If it doesn't specify, it depends on the question. You don't very often get to do open-ended questions, so like if it's a multiple choice, I would assume that it would either say in the question what units it wants or in the answers given.
Okay.
All right, do we have an answer for this, A, B, or C? Greatest molar solubility? Who thinks A? B? C? Okay. Yeah. So just like we saw with our equilibrium chapter, the larger the K, the more it goes towards the product side. Okay, so if there's more products formed, that's a greater molar solubility. So if we have a larger KSP, the molar solubility is larger because more products. But there's something else to keep an eye on, because each one of these lead salts dissociates into two ions, right? So we're going to have two particles. So we're going to have lead plus carbonate. We're going to have lead plus sulfide. And lead plus sulfate. And so when you write the KSPs for each of these, in terms of X, they're each going to be equal to, their KSP is going to be equal to X squared in each case, right? If you think about going from the ICE table to writing the KSP expression, everyone make that leap? Okay. If not, take a look. Okay. So because all of those KSP expressions are the same, we can very easily compare our KSP values. But what if we have these salts? We have calcium fluoride, calcium hydroxide, and calcium phosphate. And we want to know which of them has the greatest molar solubility. Now we've got a little more work. I would tell you this is not an immediate answer. So let's walk through it. Let's do at least one of these together. So calcium fluoride, CaF2, is going to dissociate into one calcium ion and two fluoride ion. And so when we write our equilibrium expression, we're going to have calcium 2 plus times F minus squared. In terms of X, that's going to be equal to X times 2X squared, right? Just like the calcium iodate. And we end up with 4X cubed. You see answer B, the calcium hydroxide. You have one calcium, two hydroxides. It's going to follow the same pattern. Oh, forgot my equilibrium arrows. So KSP will be equal to 4X cubed. Calcium phosphate is a fun one. Ca3PO4 2. In equilibrium, we're going to form 3 calcium ions and 2 phosphate. So at equilibrium, we're going to have 3X for the calcium. We're going to have 2X for the phosphate. Oops. When we write the KSP, we're going to have calcium 2 plus cubed times phosphate squared. And so we put 3X cubed times 2X squared. And when you multiply all of that out, you get 108X to the 5th. Okay. Questions on getting to any of those? So how do we solve the question? How do we answer the question? almost a freebie. So we need to solve for x in each of these cases using the KSPs given, and then the one with the largest x has the greatest molar solubility. All right? So our last multiple choice problem was a quick one because all the ions 1 to 1, 1 to 1, 1 to 1. Now we've got two that form 4x cubed and one that goes 108 x to the fifth. And so when we solve for x, what do we end up finding? Let's do this here. So the calcium fluoride, x ends up being 2.1 times 10 to the minus 4. So you can check this later. For the calcium hydroxide, x is 1.2 times 10 to the minus 2. And for the calcium phosphate, x equals 7.1 times 10 to the minus 7. So the one with the greatest molar solubility is the calcium hydroxide. It won't always end up that the largest largest KSP is the one with the greatest molar solubility in this type of case, but it is. It just happened to. That was your question? Yeah. A more evil person could figure out the one where the KSP is smaller, but the molar solubility is greater. Yes.
In a situation though, if the coefficients are like this, can we assume that if A and B have the same setup, B has less coefficients than C?
Yeah.
Can we say that since that's going to determine the division, even if the KSP is higher, we know that B will be higher because it has less division?
Yeah, so I think what you're saying is you could get away with only solving two of those. Yes, you could do that. Because A and B have the same formula for x cubed. So if you find the one that's, we have to do it, let's do it smart. You do the smallest one, smallest KSP, and compare that to the one that's, yeah. All right, other questions? Here's another one. So another fun problem. So you're going to see this pattern of there's only so many different types of KSP you can have because we usually only see 1 to 1 or 1 to 2 in terms of the solubility of the ions. So which one of these will have 108 x to the fifth, where the x is the salt's molar solubility? And you just saw an example of that. So it's the one where you form 2 ions of one and then 3 ions of the other. So C. You can figure out E. That's a fun one too. So we've been sort of hopscotching from one solubility or one equilibrium topic to another, right? So we started out with some basic equilibrium, and then we went to acid-base, and then we did some buffers, sorted equilibrium with a different equation, not an unstable. Now we're on solubility of salts, right? But what if we just throw it all together, right? And now we think about how solubility is affected by pH. So these aren't quite as complicated as you may initially think. We're still not gonna have 2 equilibria at play. Not really anyways, when we do these problems. But we are going to need to be mindful of how pH affects the solubility of a slightly soluble or insoluble salt. So my slide here is, I want to read this one sentence and clarify what it means. So We have ions that are formed by dissolving solids, and some of those can react with water. So that's an example here with this oxalate ion. So this, if you think back to the solubility of, not the solubility, if you think back to the pH of salt solutions, that's where this is coming in. So if we dissolve calcium oxalate, oxalate ion can act as an acid and affect the pH of the solution. And so if we have an ion that's formed from a slightly soluble or insoluble salt, and that ion can affect the pH of the solution, then if we alter the pH of that solution in another way, it will alter the solubility of that salt. Okay, that's what this is trying to say. Okay? The products affect if there are products that affect the pH of the solution, so like oxalate in this case, then the pH of the solution is dependent, well, will affect the solubility of a salt. So let's think about what we have written here, okay? Here we have our calcium oxalate that's dissolving. We have formed our calcium ion and our oxalate. It's gotten equilibrium. That oxalate can react with an acid to form HC2O4 minus. Okay. So if we add an acid to this, a solution containing this equilibrium, and we form this, how does this equilibrium shift? It goes more towards the products because we're removing some of this oxalate. Okay? So some of that's going away and reacting with the acid. So if this is equilibrium 1, it shifts towards, oh, there were numbers there, I just can't see them. Shifts towards the products. Which means, excuse me, that the calcium oxalate is more soluble in an acidic solution than it would be in a neutral solution.
Fine, you put it in basic or neutral or acid. Would it be the same kind of concept? Because you just have to go again another step further where it would become -3.
Oh, we wouldn't be able to form a -3. So, yes.
What if you started with number 2 and on the last one? And then
Okay, so let's look at how we're going to approach these problems stepwise. First thing we want to do is write out the solubility equilibrium. So solid on the reactant side, and then the ions it's dissociating to on the product side. And then we're going to write the reaction of the affected ion, the one that reacts with either an acid or a base. And then we're going to determine how the reaction shifts to regain equilibrium. So hopefully I have an example here. Yeah. So writing our solubility, writing our reaction with an acid or a base, and then thinking about the way the equilibrium is going to change. So here is magnesium hydroxide, a slightly soluble salt. Dissociates into magnesium ion and hydroxide ion. What happens if we add HCl to this solution? We know that HCl completely dissociates to form H plus and Cl minus. How's H plus going to react? Yeah. Absolutely. It's going to react with the OH minus. What are we gonna form? Water. So what happens to the solubility? Increase, decrease, stay the same? You're pointing that direction. That means products. So it increases the solubility, right? Yeah, this is going to increase the solubility. Our acid is going to react with the base that's formed. That draws that product out of the solution. The Galilein's principle says we have to form more products to regain equilibrium. Should we make up a problem on the fly? That sounds dangerous. Let's try it. Well, we can try one thing. Let's do it this way. Okay, so let's say we have this equilibrium, and the pH of the solution is, is that gonna work? I think it only works if it's basic. 10? You like 10? pH is 10. What's the molar solubility in a solution of magnesium hydroxide if the pH is 10? So the pH, let's say this, the pH is not coming from any of the magnesium hydroxide dissolving, all right? Is instead coming from an addition of another source of hydroxide. We can find the OH minus concentration from our pH. Anyone faster? Let's see. The pOH is 4, 10 to the minus 4. That's our hydroxide concentration. That would be an initial concentration. So then at equilibrium, we're going to have X moles per, ooh, this is a really good one. We're going to have X moles per liter of magnesium, and 1 times 10 to the minus 4, no, X plus X, plus 2X. So then we solve with our KSP. We're going to have X times 1 times 10 to the minus 4 plus 2X squared, and then we would solve for X. And we'll leave that for later. But I guess my point here is, if you have a pH, if you're given a problem where you're expected to use a pH coupled with the solubility, this is one way to do it, okay? Is it time? All right. What if we add sodium hydroxide? What happens to the solubility? Stop saying left and right edge. It's meaningless. Down. Thank you. All right, if we add hydroxide, we're adding a product. Shatley's principle says we have to form more reactants then in order to regain equilibrium, so the solubility should decrease.
I got that one.
Good work.
I got it.
Goes down. See, down was right. I think that you're going to have some problems like this, so let's go back to this problem. I did? Okay, it must be. We'll start. So, hang on one sec. We didn't quite finish this section, so we will continue.